I am going to show you a wave. So here is a straight string. You can try it at home. So if you move it up, down, move it up, down, you see some sort of wave shape. Okay? But yep, let's push it. Well, let's make it, um, yep, randomly like this. Right. Now, just note that the level of vibration, right, the level of moving up and moving down is called an amplitude. So the idea is I can decrease it. So I have a really small wave. I can increase it. So the level of vibration of the particles are up and down. So we have a higher uh, amplitude. Now here is the frequency, is how frequently is the wave. I have low frequency, so the wave is really big and long. If I have higher frequency, the wave looks like this. Okay, let's make it a little bit lower. Now let's pause it. Okay, so here is, yep. Okay, now so when I try to draw a wave, okay, what I do is, uh, well, I just screenshot the wave we have. Okay, now let me have, let's draw this wave. Okay, what I do is I have a horizontal axis, okay, which is measured in length, and, and also I have a vertical, well, let me draw it. Actually, let me draw the vertical axis here, which can be labeled as amplitude. Here. Now, um, no, then we can trace the line to draw a perfect sine wave in this case. Actually, uh, yep, let me use red for the sine wave. I can continue drawing, but when I ask to draw a wave, normally just draw one cycle of it. It will be fine. Okay, it will be okay. Then, yeah, then just make some notes. Just remember the distance, the, well, the length, this part is actually the amplitude of the wave. When I'm asking for the amplitude, this is amplitude. So if we somehow read it, it's approximately for 10 centimeters in this case, from the ruler on the left hand side. So here it is the amplitude of the wave. It means the particle moves 10 centimeters up and then 10 centimeters down. So we have this shape. Okay. Now, the important part is this. The length of one cycle of a wave, okay, is called the wavelength. It has a symbol of lambda, Greek symbol. So when you say I'm writing down the symbol, you mean I'm talking, you know that I'm going to talk about wavelengths, okay, which is measured in meters, centimeters, or millimeters. Now, let's go back to this simulation again. Okay, this time I'm going to start the wave soon. Okay, but this time I'm going to ask you to just concentrate on looking at maybe let's look at this green particles. Okay, let's look at these green particles there. So the green particles move up and move down, move up, move down, move up and move down. Okay. So if I'm going to draw a graph, so if I'm going to draw a graph of the amplitude, let me start like this. So if I'm going to draw the graph of the amplitude of the wave, and well, basically let's use this. Okay. The position of that green particle versus time in seconds. Okay. Now, just compare with the wave we drew. Okay. Sorry, the graph we drew before is amplitude, which is measured in centimeters, compared with the wave with the length of the actual wave, which is the wavelength measured in centimeters again. Now this time, I'm going to draw a graph of a position of that little green particle over time. So if I'm going to, well, actually, let's have a look at it again. Okay. This little green particle. Okay. It starts from 0, move up, move down, move up, back to 0, move up, move down, move up, move down. So if I'm going to sketch the vertical position versus time, I will ending up with a graph like this. Okay. It starts from 0. As time passes, it moves up. Okay. Then it moves down. Okay. Then it moves further down. Well, return to its original points here. Then it moves further down. Then moving up, returning to its original points. Then it will do the same thing again and again over a period of time. So in this graph, okay, looks similar than what's here, but just mind the horizontal axis is different. Okay, in here we have the wavelength, which is the length. Okay. In this graph is the time. Okay. Now, the important thing is the y-axis, the position should be in centimeters, is still the amplitude. However, the length indicates the time, and the time here is basically the time needed for the wave to travel one wavelength. We call that a period. We call that a period. It's the time. Okay, it's the time that a wave need to travel one wavelength. Okay, I just write a lambda for wavelength. The energy need this much of time to travel one wavelength of yep, this we call it a period. And the other thing I would like to introduce would be frequency. Frequency is basically how many cycles or how many period okay, in a second. Now let's go back to the simulation. Say we have frequencies and yeah, let me write down it. The period is measured in seconds, frequency is measured in hertz. So just remember this is simulation, it's a little bit different. So if I put down the frequency as say 2 hertz, it means every seconds, let me show you. No, this 2 doesn't show, but well, the unit is not that good. But anyway, well, forget about the unit, forget about the number there. Say if this is a wave of 2 hertz, it means in every second the wave goes into period. So in every second there are 2 cycles of wave going through. If I increase the frequency, say I increase it to 4 hertz, then it means in every second there are 3 cycles of wave passing through. That's frequency, and it's measured in hertz. Yeah, just one more important thing about the formula of frequency. Okay. So frequency in hertz can be calculated by 1 divided by the period. Say if the period is 0.5 seconds. Okay. If the period of the wave is 0.5 seconds, then it means it takes half second for wave to travel through one wavelength, to travel through one cycle. Okay, so the frequency will be 1 divided by 0.5 seconds, okay, which is going to be 2 hertz. So in every second, there will be 2 periods. Okay, so make a note of that. We're going to deal in a lot with frequencies in physics.